Yeah, the screen is fine, right? It is visible, right?
Can you zoom in?
Yeah,
Oh, okay, fine.
just
Yeah.
zoom.
Yeah. So first of all, I'll just mention what I'm going to do. So I'll be first of all mentioning a theorem called Atkinson theorem. So I'll give three equivalent conditions for the definition of a Fredholm operator when an operator is called Fredholm. That is the Atkinson's theorem. And then I'll define something called Calkin algebra. So basically, okay, fine. I'll define it. And essential spectrum. And so these are the topics that I'm going to do today, and Fredholm index.
So what is Arka going to do? Do you know that?
After this, so I just go till that index definition and a bit of results after that. And then he goes to prove that index of some t plus a compact operator. If t is Fredholm, then index it is that index is equal to index t. Such results are there. So those he will prove from there. So I'll be proving till some like half of the this one. I mean till okay. Yeah, I'll just mention. So first of all, what is a Fredholm operator? So a Fredholm operator is to give an intuitive idea. So it's an operator that is invertible up to a compact operator. So there are three equivalent conditions, and this is called like Atkinson's theorem. So if there exists Si, let T belongs to B of H1, H2 is called Fredholm. If there exists Si belongs to B H2, H1, and a compact operator Ki in B H1 and I mean K1 is in B of H1 and K2 is in B of H. I mean compact operator of H2, such that these equations are satisfied. So what I'm trying to say is here is S1T is the identity operator of H1 up to a perturbation in K1, up to a perturbation by compact operator K1, and okay, this should have been H2 actually. So TS2 is equal to 1H2, I mean identity of H2 plus K2, and this is equivalent to the range of T being closed and dimension of kernel of T and dimension of kernel of T star being finite. And this is equivalent to the map identity of H1 minus, okay, so there is this is equivalent to the existence of an S such that ID of H1 minus ST and ID of H2 minus TS are projections with finite dimensional range. Yeah. So as I said, the intuitive, I mean, like the idea of a Fredholm operator is for this operator T to be invertible up to a perturbation by a compact operator. So here there is a left inverse, and S2 will be a right inverse. There should be S2. And here we will see that this compact operator, we can see that it is actually a finite dimensional projection. And this is an easier way to like see if an operator is Fredholm. Yeah, so I'll prove this theorem first. Yeah. So first of all, 1 implies 2. So we consider a finite rank operator F such that K1 minus F is less than 1 by 2. And since K1 is compact, such a finite rank operator exists. I mean, like K1 is the norm. K1 is in the norm closure of finite rank operators. So let M be the kernel of F, and what we will get is that we will get that S1, this inequality holds. So S1 TX is less than or equal to S1 TX, and this S1 T is equal to identity plus K1. So this is true. And then here K by S up Fx is equal to 0 because S is in kernel of F. So this is true. And then what we get is this inequality. Since we have chosen F to be such that K minus F norm of that is less than 1/2, we will get that the whole thing is less than 1/2 norm of X. So what we have done is we have bounded the operator T by bounded below. I mean, we have bounded the operator T below. So since it is bounded below, we have that the image is closed. Yeah. So yeah. So we have that T of M is closed in H2. This is a result like we have proved in class. So T of M is closed in H2, and now F restricted to M per M was the kernel of F, so F restricted to M per is injective, and the dimension of range of F is less than I mean dimension of range of F is finite because F was finite rank operator. So what we have is that M per is a finite subspace, finite dimensional subspace, and so is its image. So basically we have this one is a finite dimensional subspace, and this one we have that it is a closed subspace of H2. So sum of a closed subspace with a finite dimensional subspace is again closed. So range of T will be closed. This is the range of T, right? Because like M direct sum M per is the whole of H1. So range of T is closed. So we got the first this thing, second part. So we got that range T is closed. And again, for this part, if H is in kernel of T, what we have is K1 of H is equal to minus H, and we will have that kernel of T is contained in range of K1. So and we know that kernel of T is closed. This will imply that dimension of kernel of T is less. I mean, it is finite, and so this is a result. I mean, this is a property of compact operator, and similarly, kernel of T star is contained in range of K2 due to similar reasoning, because we have this equation T of S2 is equal to okay, wait. So from that we will get that kernel of T star is contained in range of K2, and this will imply that dimension of kernel of T star is also finite. So yeah. So range is closed, and the kernels are kernel of T and T star is finite dimensional, which is a second condition. And for 2 implies 3, what we do is let N1 be kernel of T, N2 be kernel of T star, and n1 perp is going to be range of T star because h1 is kernel of T direct sum. I mean, h2 is kernel of T direct sum range of T star. Yeah, and yeah. Oh wait. Oh, okay. H1 is kernel of T direct sum range of T star, and the other way, like H2 is kernel of T star direct sum range of T. So, so what I'm doing is we restrict T to the n1 perp range of T star, and since it is perpendicular to, I mean, this n1, it is the perp of kernel of T, it is injective, and we restrict it to like we restrict the image to n2 perp. Again, this is a closed subspace and it's a Banach space. So what we have is that this injective operator that is subjective. By open mapping theorem, we will have that it has an inverse S0. So what we do is we define S to be the operator S0 composed with the projection P on n2 perp. So this is a map from H2 to, so projection of n2 perp takes H2 to n2 perp, and composing it with this, it will take to n1 perp, and we can consider n1 perp to be the a subspace of H1. So this thing belongs to B of H. So this is an operator from H2 to H1. So we have to prove that this T composed with S is actually a finite dimensional, finite rank projection. So Ts is equal to T of S0 composed with P n2 perp, and T of S0. I mean, so if I'm applying some, so if I am applying some T, some H plus Y, this one in N2 and this one in N2 perp, what happens is, yeah, this is T S naught, this was S naught, and this is going to be T S naught Y. So T S naught restricted to N2 perp, this was identity map of N2 perp. So because we defined S naught to be the inverse of T in N2 perp. So what happens is this is Y. So we can see that this map actually is the T S naught P N2 perp. This one is P N2 perp. And this is equal to 1 of H2 minus P N2. Yeah. So so this is our requirement, because okay, N2 was finite dimensional because N2 was kernel of T star, and by the second condition, I mean, dimension of kernel of T star is less than infinity. So so what we have is that Ts is some this identity minus a projection that is finite rank. So it is in our required form. Similarly, we can do this for ST. So S will be S naught Pn2 perp, and we can do the similar thing to get this operator to be Pn1 perp, and which is equal to 1h1 minus Pn1. And again, n1 is kernel of T, and it is finite dimensional from second condition. Okay, so for the 3 implies 1, what we can do is we have that TS is some TS is equal to identity on H2 minus a projection on a finite dimensional subspace. So this projection itself, this one is itself is a finite rank operator and it is compact. So it's clear that it is of the form this form. I mean, it is this form. TS2 is equal to 1H2 plus K2. S2 and S1 both are S here. Yeah. So we had TS is equal to 1H2 minus PN1, and this one is a compact operator. Oh, this one is a compact operator because it's a finite rank operator. So this form is clear, and the other way is also clear because ST. Okay, there is no bar there. So sorry. So ST is equal to 1H1 minus P. Okay, wait. This should be N2, I think. Sorry. And this one is P N1. Again, this one is also compact operator and it's in the first form. Yeah. So these are the 3 conditions are equivalent, and Atkinson's theorem is proved. So yeah, as I said, any operator satisfying these 3 equivalent conditions is called a Fredholm operator. Yeah. And now again, so a Fredholm operator is an invertible an operator that is invertible up to a perturbation by a compact operator. And so okay, so this is some small remark. So the collection of Fredholm operators from H1 to H2, that is denoted by this thing, F of H1 H2. So this collection is non-empty if and only if both H1 and H2 are either finite dimensional or otherwise both are infinite dimensional. So so in the case of finite dimensional, what happens is every operator is a Fredholm operator because range T will be closed. Range T will be a subspace. It is finite dimensional. It is closed, and kernel T and kernel T star both are going to be finite dimensional. So any operator is going to be Fredholm, and in infinite dimensional. Okay, so we are assuming H1 and H2 are both separable. So in that case, what we can do is we have an orthonormal basis, so we can take the base elements to base elements as a bijection, and this gives us a operator that is Fredholm. Again, this way also can be proved. I mean, okay, to prove that. Yeah, so yeah, suppose we have a Fredholm operator, I mean T, then if the range if the image H2 was finite dimensional, then what it means is range of we know that we will have that range of T is sorry, we will have that kernel of T is going to be infinite dimensional. This is because kernel of T is range of T star. Okay, wait. And this is finite dimensional. So if H1 was infinite dimensional and H2 was finite dimensional, then we will have that kernel of T is an infinite dimensional subspace of H1, contradicting that T was Fredholm, because we needed kernel of T to be finite dimensional. And in similar way, like if H1 was finite dimensional and H2 was infinite, we will have that kernel of T star will be infinite dimensional. Again, contradicting Fredholmness of T. So this remark is true. Yeah. So now I'm defining something called Calkin algebra. So I had mentioned Fredholm operator is something that is invertible up to compact operator. So what we do is we quotient the collection of operators on H from H to H by the compact operators on H. So and this quotient is called the Calkin algebra. This so if pi is the quotient map, we will have that the collection of Fredholm operators is the inverse under quotient map of the collection of invertible elements of Calkin algebra. Again, this part is clear. I mean, it comes from the Atkinson's theorem, because is this clear or should I explain more? Okay, maybe. Yeah, I'll go.
So every operator, every Fredholm operator is invertible when we reduce it modulo the ideal of compact operator, right?
Yeah, exactly. That was yeah. So that was the
first
what
condition.
Yeah, that was the first condition. So S1 is the left inverse of T, and S2. This should I mean S2. S2 is the right inverse of T up to a compact operator. In this one K1 and this one K2. And this is in this case we are just saying that it need not be compact itself. It can be a finite dimensional range projection only. And this second one is an easier way to identify which operators are Fredholm, because computing range T and kernel T star, that is easier than doing this and explicitly finding S1 and K2. Yeah, so that was the idea. And yeah, so this part is clear, right? Or maybe okay. Then I'm moving to essential spectrum. So essential spectrum is again the collection of complex numbers in which T minus lambda does not belong to f of s. So basically, this is just saying that pi of T minus lambda is not invertible. So basically, we are looking at the spectrum of pi of T, we can say, in a sense. So yeah, so what we are saying is T minus lambda does not belong to f of h. F of h is pi inverse of g of qh. If and only if pi of T minus lambda does not belong to g of q of h. This does not belong to g of q of h means pi of T minus lambda is not invertible in the Calkin algebra. Yeah, so Calkin algebra is a C-star algebra, but and we haven't proved that in the textbook. C star structure. How does the involution structure comes in? What I just mentioned. Okay. So now I define something called a Fredholm index. So if T is a Fredholm operator from H1 to H2, then index of T is just the difference between the kernel of T, dimensions of kernel of T and kernel of T star. We have, from the second condition of the Atkinson's theorem, we have that both these are finite dimensional. So this is what index of Fredholm index of T is defined as. And now I mention some results and things about the index and all. So first of all, if T is a Fredholm operator from H to H, H is Hilbert space, then and if T is normal, then we will have that index of T is 0. So the reason is we will have that T star T is equal to T star. So this will mean that mod of T square is equal to mod of T star square. Yeah, so mod T is equal to mod T star. Because the square root is unique. So, and now we know that kernel of T is equal to kernel of mod T for any operator T. I mean, from the polar decomposition. So, yeah, the way we do is this, like norm of Th square is equal to norm of T. I mean, this thing, Th comma Th, which is T star Th comma H, and this is actually mod of T square H comma H, and this we take it here, so we get this. So we get that norm of mod T H whole square is equal to norm of Th square. So we will have that kernel of T is equal to kernel of mod T. So this one is true. And we just proved that kernel of mod, okay, we just proved that mod T is equal to T star here, mod of T star. So the second equality is also true. Yeah, this one is also true. And similarly, since we showed it for any operator, kernel of T, mod T star is equal to kernel of T star. So kernel of T and kernel of T star has the same subspace. So we will have that their dimensions, difference of their dimensions is 0, which was the index. Yeah. Now, suppose for a Fredholm operator, if the both Hilbert spaces H1 and H2 are finite dimensional, then I mentioned that any operator is from H1 to H2 is going to be a Fredholm operator. Because range T is a finite dimensional subspace, it is closed, and kernel T and kernel of T star both are finite dimensional, so it is Fredholm. And I'm saying that index of T in that case is dimension of H1 minus dimension of H2. So irrespective of what the operator is, the index is going to be fixed certain. It is just depending on the dimensions of H1 and H2. If H1 and H2 are finite dimensional. So to prove this, yeah, we remember the rank-nullity theorem. So dimension of H1 is equal to dimension of kernel of T plus dimension of the range. And same for T star. Similarly for T star. And here, T, we know that in the finite dimensional case, T can be represented as a matrix, and T star is the conjugate transpose of that matrix. So their ranks are going to be the same. So we will. So this rank of T is actually the dimension of range of T, and rank of T star is the dimension of range of T star. So what we have is that these both dimensions, dimension of range of T and dimension of range of T star, is going to be the same. So what we have is the dimension of kernel of T minus dimension of kernel of T star is just dimension of H1 minus dimension of H2. These two terms get cancelled because they are equal. Yeah, so this is true. Now, suppose S and T are operators. S is an operator from H1 to some Hilbert space H4, and T is from H2 to H3. So there are four Hilbert spaces, four spaces here. And U and V are operators that are invertible. So in that case, S being Fredholm is equivalent to saying that T is Fredholm. And in that case, index of S is going to be equal to index of T. So again, proving this, for proving that, what we do is U and V are invertible. So this is an operator. Yeah, so they being invertible means that first of all, these are bounded operators, so they form homeomorphism when they are invertible. So they take closed sets to closed sets. So what we have is, if range T is closed, okay, if range S is closed, then it is equivalent to saying that range T is closed. And similarly, U and V forms some vector space isomorphism. From that, we will get that dimension of kernel of T is the same as dimension of kernel of S, because kernel of T and kernel of S will be isomorphic as vector spaces. And similarly for kernel of T star and kernel of S star. So if S is Fredholm, then range of S will be closed and range of T will be closed then. And kernel of T will be finite dimensional. So kernel of S will be finite dimensional. Kernel T star will be finite dimensional, which will mean that kernel of S star is also finite dimensional, and vice versa. Okay, wait. I said the other way, I think. Kernel of S is finite dimensional, which will mean that kernel of T is the finite dimension. And similarly, and vice versa. So S being Fredholm is equivalent to saying that T is Fredholm. And index, so if one of them is Fredholm, both are Fredholm, and then indices will be the same because again, dimension of kernels is going to be the same, and dimension of kernel of T star is equal to dimension of kernel of S star. So their differences are going to be the same. So index is equal to index in T here. Yeah. So now suppose we have two Hilbert spaces H1 and H2, and H1 is the direct sum of some closed subspace N1 and closed subspace N1, such that dimension of N1 is less than infinity, so it is finite dimensional. And similarly for H2, it is a direct sum of N2 and M2, and dimension of N2 is also finite. In that case, and suppose T takes N1 to N2 and M1 to M2, such that T restricted to M1 is an invertible map. So T will look like this. It looks like some operator A from N1 to N2, and some invertible operator D from M1 to M2. So what I'm saying is, in this case, T will be Fredholm, and index of T is going to be the same as index of A, which is, since A is from finite dimensional space to finite dimensional subspace, which is finite dimensional closed subspaces. we will have that it is equal index of A from the previous result. This result, index of T is equal to dimension H1 minus dimension H2. From that result, we will have that index of T here is dimension of N1 minus dimension of N2. Okay, wait, sorry. Yeah, dimension of N1 minus dimension of N2. Yeah, so to prove this, range of T is T of M1 plus T of N1, and T of M1 is just M2. It's a closed subspace, and T of N1 is a finite dimensional subspace. So it is also closed. So sum of a closed subspace with a finite dimensional subspace, it is again going to be closed. Should I prove that here, or is that clear? Maybe I'll prove. So what I'm saying is M1 is a closed subspace, and so T of N1. Okay, sorry. This M2 is a closed subspace, and T of N1. This one is a finite dimensional subspace. So actually, this was a direct sum. There was no intersection. So what we can do is we can take the quotient by M2. Yeah. Since M2 is a closed subspace, it is possible, and this will be a finite dimensional. The image will be finite dimensional because T of N1 itself was finite dimensional. So there. Okay, yeah, so what I'm saying is if we quotient the whole of H2 with respect to M2, the image of N1, T of N1 is finite dimensional, and if we take the so it is closed. So if we take the inverse of that, that is going to be this space. So it will be closed since the quotient itself is continuous. Yeah. So we have that range of T is closed, and now also kernel of T is equal to kernel of A. Why is this true? Because D, the operator D here, this was invertible. So kernel can only belong to the, it will be contained in the N2, and it will actually be equal to A. Yeah. So kernel T is equal to kernel of A. And similarly, T star is going to be this matrix, A star times B star. And kernel T star is going to be kernel of A star. So for a Fredholm operator T, we have, okay, so kernel of A star is also finite dimensional because kernel of A star is contained in N2, and kernel of A is finite dimensional because it is contained in N1. And so we have that T is a Fredholm, its kernel of T star, and range is closed. Kernel T are finite dimensional, range T is closed. So we have that T is Fredholm by the second part of Atkinson's theorem. And their index of T is going to be the difference of these things, which is difference of dimension of kernel of A and dimension of kernel of A star. And yeah, which is the index of A. We proved index of A to be, in the finite dimensional case, we proved it to be dimension of N1 minus dimension of N2. Yeah. Okay, one more thing. So should I, this kernel of T is equal to kernel of A, is that fine, or I mean, I didn't actually show the proper this thing. Should I write it or should I? Is it clear again?
It's okay. Write it, no? Better.
Okay, fine. I'll write. Yeah. So oh, sorry. Yeah. So our H1 was N1 direct sum M1, and H2 was N2 direct sum M2. So if H plus Y with H being in N1, Y being in M1, if this was in kernel of T, what happened? This would have mean that T of H plus Y is equal to 0. But we know that T is of the form matrix of this form, A and D. So what we have is A is plus dy is 0. Now AH is in N2 actually, and dy is in M2 because A takes N1 to N2 and D takes M1 to M2. So they are 0 independently. So this, since B is invertible, this means that Y is equal to 0. And this means that X belongs to kernel of T, kernel of A. So X plus Y was actually just X, and this X actually belongs to kernel of A. So this part is clear. Kernel of T is contained in kernel of A. This part is clear. And for the other part, if X was in kernel of A, if H was in kernel of A, again, this is in N1. So if you apply T of H to it, this is equal to AH because it is an N1. And this is equal to 0 because it is an N1. So again, H belongs to kernel of T. Yeah. So kernel of A is contained in kernel of T. This is also clear. So kernel of A and kernel of T is equal. That is okay. Yeah. So yeah, for a operator, that's known as a lemma. Again, we are what we are trying to do is we are trying to relate to operator T. So we are trying to relate an operator T to a operator from a subspace to a subspace of H2 A. I mean, okay, we are trying to relate it to this operator actually, where okay, fine. I'll just mention it. So let Hi be of the form Ni direct sum Mi. These Ni's are Mi's are closed subspaces S equal to 1 to 2. Then T is of the form A, B, C, D. A is an operator from N1 to N2. B is from N1 to M2. C is M1 to N2, and D from M1 to N2. Yeah. So if D is invertible, this T is Fredholm if and only if the operator A minus BD inverse C is Fredholm. And their indexes will be equal if they are Fredholm. And again, in the case where dimension of Ni is finite, in that case, we will have that index of T, which is equal to this index of this operator, is going to be dimension of 1 minus dimension of N2. Because in the finite dimensional case, the index is just dimension of the domain time minus dimension of the codomain. So yeah, we are trying to relate these two operators, being Fredholm as an equivalent condition for these two operators. So yeah, I'll prove. The proof is this. First, what we are trying to do is we consider this operator U, which is from H2 to H2. This operator is invertible. The inverse is this. And V is an operator from H1 to H1. This is also invertible. Again, inverse is just this 1 and 1. And instead of minus here, I'm doing D inverse C. So what we have is, if you compute this, we will have that U T V, U composed with T composed with V, will be of the form A minus B D inverse C, and 0 here, and the here it will be D. So it is similar to the case we did before. D is an invertible operator, and this is an operator here. So we had proved earlier that if U and V are invertible, then UTV is a Fredholm if and only if T is Fredholm. So that is what we use here. And also, range of UTV is closed if and only if range of A minus B D inverse C is closed. So why is this true? This is because so we want to prove that range of T is closed if and only if range of A minus BD or C is closed. So T of H1, which is a range of T, is actually T of oh wait. Oh, sorry. This is not a T here. It is UTV. So there should be UTV. UTV. Maybe I'll write it as this or something. Yeah. This is S of N1 plus S of M1, because as we saw, it is of the form some diagonal matrix. So it takes N1 to N2 and M1 to M2. And S of N1 we saw that it is A minus BD inverse C and of N1. And this one is, okay, wait. This one is D of M1, which is actually M2 because D is invertible. So if this, and this one is a direct sum actually, because like their intersection, this one is contained in M2 and this one is contained in M2. Their intersection between the two set is actually 0. And they are orthogonal complements also. So this is a direct sum actually. So if this is closed, so if X and yn are sequences in this direction that converges to some xy, then xn converges to x in this set, and yn converges to y in M2, and xn converges to x, and this is a closed set. That will mean that x is in this. So what we will have is xy is also contained in this direct sum, which is S of h1. So we have that if this is closed, then this one is closed. And also what we can see is that if this one is this set image a range of S is closed, then we can intersect it with the closed subspace N2 to get this set. So intersection of range with the closed subspace N2 is this one. So it is also closed. Yeah. So range is being closed is equivalent, and the kernel is also equal. Kernel of UTV is equal to kernel of A minus BD inverse C by a similar reasoning as I mentioned in the last proof. For the yeah, we proved here, right? For this A and T, due to a similar reasoning, we will have that the kernels are kernel of T is just the kernel of UTV is actually kernel of A minus BD inverse C, and similarly kernel of UTV star is going to be the kernel of A minus BD inverse C star, because UTV star is going to be this one. Yeah, proving UTV star is equal to this matrix is again we use the definition of adjoint and show that it is the same, because yeah. So if it was some T x1 plus h2 y, and this is so it is A minus BD inverse C of h1 plus D of h2. Okay, x1 was in n1 and this one was in m1, and y, and this is equal to yeah, so A minus BD inverse C x comma y plus the other term dh2 comma y. We can take their adjoint. So what will happen is s1 A minus BD Yeah. Okay. A minus BD inverse C Y, okay, star plus H2 D star Y. So yeah, so what this one is actually contained in this one is contained in N1, and this one is contained in M1. Okay, wait. Yeah, so what I'm saying is I'm saying adding this H2 here doesn't change the thing, because inner product of H2 with this one is again going to be 0. Again, similarly for here, it's adding N1 H1 here will not change anything. Oh. So what we have is it is X times the sum of this one, A minus B D inverse C star. Oh, okay. Okay, it should be Y1 here actually, and Y2 here, because yeah, because A minus BD inverse C is a map from N1 to N2, and it only acts on, okay, Y1 is in N2, and this one is in M2. Yeah. So we will have that this is Y1 plus D star Y2. So and yeah, so it is of the form H comma sum action of this operator. So what we have is this T star of Y is of the form A minus BD inverse C Y1 S star Y1 and the D star times Y2. Yeah, so this is of the form of that operator. I mean that matrix form. So so what I did here was I showed that kernel of UTV is the kernel of this operator. UTV kernel of this, or UTV star is the kernel of this operator, and the ranges of this one is closed if and only if range of this one is closed. So UTV being Fredholm is equivalent to saying that A minus BD inverse C is Fredholm. And we had shown that T being Fredholm is equivalent to saying that UTV is Fredholm. So both these conditions will imply that T being Fredholm is equivalent to A minus BD inverse C being Fredholm, because T being Fredholm means that UTV is Fredholm, which means that A minus BD inverse C is from Fredholm. And again, index of T is going to be UTV. We have proved this before. U and V are invertible. So index of T is index of UTV. This, okay, where is that? Oh, yeah, this proposition. I mean this result. Yeah. S is equal to UTV, then index of S is equal to index of T, and they are S being Fredholm is equal to T being Fredholm. So and index of UTV is equal to index of A minus BD inverse C. Again, this one we have proved, because A minus BD inverse C is a from N. I mean this one, yeah, this one so we have proved before. So if dimension of ni is finite, we will have that this index actually here. This one will be dimension of n1 minus dimension of n2. Yeah. Okay. So these are the main results, and now I mention some some exercises that was there in the book. So if it's a Hilbert spaces H1 and H2 are of the form N1 direct sum M1. H1 is of the form N1 direct sum M1 and H2 is of the form N2 direct sum N2. Then if an operator T is in this form, then with A and D being invertible, then T is invertible with the inverse being this one. This can be just checked by just multiplying this up. We can see that it actually turns out to be identity. And for this one, this is similar to the result I did before. So instead of the diagonal elements, if T is of the form 0b C0 with B being invertible, then T being Fredholm is equivalent to saying that C is Fredholm. So meaning that B is invertible. And in this case, in the case that these are Fredholm operators, then index T is equal to index of C. The proof is similar to the one we did before. Instead of it being on the diagonal elements, we have to just do it for this one. Range will be the same for range will be closed if range of C will be closed if and only if range of T is closed, and kernel of C will be equal to kernel of T, and kernel of C star will be kernel of T star. So T being Fredholm means that the same is true for C, and index also will be the same as the kernels are the same. Yeah, and this was another exercise that was there in the book. So if phi is a locally constant function from closed interval 0, 1 to integers, then it is constant. So this is not directly related to this stuff, but it is going to be used in one of the results Orko is going to prove, I think, for the index calculation. I mean, index, something related to index. So I'll just briefly mention what this is. So, so one thing here is we are not assuming that phi is not continuous. So to do that, it is locally constant. So if take some phi of x1, some point in the image of phi, and we define v to be all the x such that phi of x is equal to yeah. First, we take some y in the range of phi, and we define v to be the collection of points where so such that phi of x is equal to y. This y is fixed; it's an element of range of phi, and we define u to be the complement of. So s belongs to 0 1 says that phi of x is not equal to y. So since at any point x where it is phi of x is equal to y, there is a neighborhood around x such that phi of x dash is equal to y for any s dash in that neighborhood. So it is this V is the union of such neighborhoods. So it is an open set. And U is also something similar can be done. So for any so any point in U can attain some yeah. So if y dash is in phi of U, then it is phi inverse of y dash. Actually, this V was actually phi inverse of y. So again, this phi inverse of y dash is open due to a similar reason, because any point that has phi of x dash is equal to y dash, phi of x is equal to y dash, it has a neighborhood where the value of phi is y dash again. So this is an open set. The union of them is an open set. U is also an open set. So we have U and V are both open set, and their union is whole of 0, 1. So so to disjoin union of two open set is a connected set, which is a contradiction. So we will have that this, unless U is empty, this will be a contradiction. So we will have that U is a empty set. So every element will be having the same phi. Phi is a constant function. And there is some other results, some exercises mentioned again. So if T is an operator and U mod T is the polar decomposition, then T being Fredholm is equivalent to saying that U and mod T both are Fredholm. And a partial isometry of is Fredholm if and only if the initial and final space have finite coordination. So these exercises, I actually I'm not mentioning the proof. I'm just mentioning the result because yeah, it wasn't done in the text, and I haven't properly worked out the details either. And again, so an operator from H1 to H2 being invertible. So the collection of such operators is an open. So there is an epsilon greater than 0 such that norm of D minus D naught is less than epsilon. Then D is also invertible. Again, this can be proved from taking the polar decomposition of D naught and writing this norm of D minus D naught as some norm of U star D minus mod D naught, where U naught is the polar this partial isometry. And we can use the fact that invertible operators in B of H1. This one is in B of H1, and this one is also. So these are open. Using the result, we can prove that. Again. Yeah, so if U mod T is the polar decomposition of T and T is normal, then saying T is Fredholm is equivalent to saying that there is a some decomposition where T looks like T1 direct sum 0, where T1 is an invertible operator and normal, invertible and normal. And this is also equivalent to saying that there exists some epsilon greater than 0 such that this condition is satisfied, where P naught is some finite rank projection. Yeah, so there is another result where like lambda being in essential spectrum of T, this is being classified here. So again, lambda does not belong to essential spectrum of T, means that there is a decomposition where T looks like T1 directs some lambda, with T1 minus lambda being invertible unknown one. And this is equivalent to saying that there is some epsilon greater than 0, where this one is true. Here, P lambda is a finite rank projection, and D epsilon plus lambda is the unit disk. Epsilon disk around 0 translated by lambda. So it is epsilon disk around lambda. And this is the projection. I mean, it is a projection function to the subspace. So these are three current conditions. Again, I'm not proving it now, but I'm just mentioning it. So yeah, that's it. Thank you.
Yeah, so too many things to digest, I think. So any questions? Or we can discuss it later also. You can go through the presentation in YouTube. Anyway, if you have any question, you can ask me. Okay, as there.
Some of the results I had to rush through, like properly writing it down.
You went slowly, it's fine, it's okay. You went slowly, but there are too many things, that's all. Okay. You did a good job, good. Okay. Okay then, so I will stop the session.